Alright guys, here we are in 8.1.3, or sorry, 8.1.6. We're going to talk about exponential functions. Exponential functions are a really important family of functions. You see exponential growth and exponential decay all over the place in the world. Anytime you have a biological population that is usually growing exponentially, you can have exponential decay. Literally, when something decays, if you have a tree that's rotting and you measure its mass, it's going to the mass is going to decrease exponentially as the tree rots. You have pollution in rivers that get diluted, and that dilution can be modeled with exponential decay. This stuff shows up all over the place in the real world, and we're going to talk about those exponential functions right now. So an exponential function is in the form of y equals ab to the x, where b is greater than 0 and not 1, and where a is not equal to 0. If your a equaled 0, just think about this real fast. If your a equaled 0, the whole thing would equal 0 because you're multiplying by 0. If your b equaled 1, well, you would just be raising something to you'd be raising 1 to some power, and that would always be 1, because 1 times 1 is 1, and 1 times 1 times 1 is 1, and 1 times 1 times 1 times 1 is 1. So then that would just give you your a value. So we put a couple little restrictions on there, but they're not too hard to remember. Note that the variable x is the exponent. So having the variable in the exponent is what makes it an exponential function. So 2 to the x is an exponential function. Exponential function. Whereas x squared is a polynomial function. And not an exponential function. So in order to be an exponential function, we need to have the exponent as the variable. Okay? So we're going to go down here and look at our first example. All exponentials in this form have the x-axis as an asymptote. We talked about asymptotes a few videos ago. This is a line down here that our function is approaching but never quite reaching. And we're getting closer and closer to y equals 0, or the x-axis, but it never quite gets there. The coefficient a is the y-intercept, or the initial value. All right, for example, a equals 3 for the function. Y equals 3 times 2 to the x. So again, if we're following our format, a, b to the x, a is 3, b is 2. Therefore, in the table and graph of y equals 3 times 2 to the x at the right, 0, 3 is the y-intercept. Okay, and we see that right here. 0, 3 is the y-intercept. And in this case, we're doubling each time period, which means that when we double the 3, multiply by 2, we get 6. So then our next point is going to be 1, 6. We multiply that by 2, we get 12. So now we're at 2, 12. If we go back a step to negative 1, we're going to be half of that, because we're going to divide by 2 now. And that's going to put us at 1.5 when we go to negative 1, which we have right here. And half of 1.5 is going to be 0.75, which is this point right here. And connecting those dots gives us our graph. The base b is the multiplier for each additional unit of the x value. The previous y value is multiplied by b. For example, in the table on the right, the multiplier is 2, and we just sort of went through that. For values of b greater than 1, the function increases. So if you have a b value that's over 1, you get exponential growth. So I'm going to write the word growth here because it's really associated with exponential functions. And exponential functions that have exponential growth always look like something like that without, let's be careful about that. There's an asymptote there. They're going to grow like that. And this is known as exponential growth. Yes. When the b is between 0 and 1, or other words, it's a fraction or a decimal that's less than 1, still greater than 0, the value of the function decreases, and it's called exponential decay. And it looks like this. So we start high, we go low as we go to the right. In applications of exponential decay, sometimes we refer to half-lives. Half-lives mean that the multiplier, the b, is equal to 1/2. And half-life is the amount of time it takes for half of the original amount of whatever it is to remain. So in problem 8-56, you saw that the half-life of radioactive carbon was 5,730 years. In other words, it takes 5,730 years until half of the original amount of the C14 remains, no matter how much you started with. So if we had some problem that was, if we started with, 20 grams of C14, we would have a multiplier of 1/2, and we would think about, I'm going to put a little lambda there, that's the half-life, of how many half-lives we've gone through in order to get some amount of carbon. Maybe I'll change that to x just to stick with what we're used to. So x in this case is the number of half-lives so if we wanted to know how much it had gone through, how much was left after 4 half-lives, we would say y equals 20 times 1/2 to the 4th power, and that would give us 20 times 1/2 to the 4th power is 1/2 times 1/2 times 1/2 times 1/2, which is going to be 1/16. So we would have 20 over 16 grams, which would be 10/8, which would be 5/4, which would be 1 1/4 grams of C14. If we wanted to know how much time had passed to go from our initial value of 20 grams to 1 1/4 grams, we would have to take the 4 half-lives and multiply it by that many years, because each of those years is 5,700, and each of those half-lives is 5,730 years. Okay. Finally, there's a little line down here at the bottom that says geometric sequences are special cases of exponential functions in which the domain is restricted to positive integers. So if we had our series, something like 2, 4, 8, 16, 32, 64, this is a geometric sequence. We're doubling each time. One, 2, 3, 4, 5, 6. That is would get plotted as an exponential function with discrete values, so we would get little dots that would go up in an exponential growth type way. All right, so let's look at the problem I have for you to end the lesson with. A rancher hires a biologist to monitor the coyote population on her land. I'll edit there. In the first year, the biologist counts 12 coyotes. The second year, there are 18. The third year, there are 27. If growth continues exponentially in this way, how many coyotes will there be in 14 years? And if you get, a decimal answer, then round to the nearest coyote. I'll give you a little hint here. Start by finding A, the initial value, and B, the multiplier for this situation. So because we need to find A, which is the y-intercept, we need to go back and find how many there would have been in a theoretical 0 year. This is how many coyotes we had in year 1, how many in year 2, how many in year 3. So find the multiplier. In other words, what do I multiply 12 by to get to 18? what do I multiply 18 by to get to 27? That'll be my b value. Divide 12 by that number to get your a value, and then plug it into y equals ab to the x. And you're going to use, we want to know what happens when x is 14. How many coyotes do we have in that population? All right, guys, do that.